All right, I'm going to go over some of the confusing topics, at least some of the topics that people had mentioned on their discussion topic. So seasons, they are on the 21st. There are 4 of them. And the June solstice, June 21st, subsolar point is at the Tropic of Cancer. 3 months later, because it goes solstice, equinox, September 21st. 3 months later, December 21st. 3 months later, March 21st. If you read the fine print, you'll notice it's not always exactly on the 21st, but if you read the fine print, you'll know it's not always on the 21st, so I'm just going to use the 21st. It's close enough. Another important idea is that the position that's getting direct sun, the subsolar point, migrates 47 degrees from the Tropic of Cancer on the June solstice on June 21st. 6 months later, because of axial parallelism, the Earth's axis points at the North Star as it goes around the sun. It's still pointing at the North Star. And now the subsolar point's the Tropic of Capricorn, 23.5 degrees south. So another diagram showing the same thing but differently, because in this diagram you can see that the position of, well, the relationship of the axis to the North Star doesn't change. But if you were the sun, at this point you'd be seeing more of the northern horizon. You couldn't see any of the Antarctic Circle. And on this date, you can't see any of the Arctic Circle. 24 hours of sunlight for the Antarctic, 0 hours of sunlight for the Arctic Circle. But if we were just hovering over the equator for a year, you'd see that the position of the sun moves from 23.5 north to the equator to 23.5 south. So that's 47 degrees. Going from 23.5 south to the equator is 23.5. Going from the equator to 23.5 is 23.5. So 47 degrees of movement of the subsolar point over the course of a year. Subsolar point on the June solstice, the northern hemisphere is having longer days. You can see at the Antarctic Circle they get nothing, 6:21. 6 months later, now the subsolar point is 23.5 degrees south, the Tropic of Capricorn. Another diagram showing the march of the seasons, just to reinforce again. It's every 3 months, solstice, equinox, solstice, equinox. There's those dates to remember. Solstice, equinox, solstice, equinox. Atmosphere. Yeah, I'm really happy with this. So I like this diagram a lot, and it's got the atmosphere going from the surface up to 480 kilometers, but you can see you can divide it up and look at it 3 different ways. You can look at it in terms of composition, you could look at it in terms of temperature, and you can look at it in terms of function. So some of the confusion was that, for example, the ozone layer occupies the same space as the stratosphere. So let's take a look. In terms of composition, from the surface up to 480 kilometers, it's all still the atmosphere. And by composition, we've got so here we've got composition, heterosphere, homosphere. We've got the thermosphere, in which case, in terms of temperature, we have 4 layers. We have the troposphere, we have the stratosphere, we have the mesosphere, and the thermosphere. And then in terms of function, we have the ozone layer and the ionosphere. So in terms of composition again, there's the homosphere from the surface up to 80 kilometers, where the gases are blended by mixing by wind. And then we have the heterosphere, where the gases are not mixed and they're separated out by density, with the lightest gases floating to the top, hydrogen and helium, and the heavier gases, oxygen and nitrogen, settling down towards the bottom of the heterosphere. In terms of temperature, we have the troposphere, and dividing things up by temperature, it's important to keep in mind not just the temperatures, the troposphere going from 15 degrees at the surface, 15 degrees Celsius, down to negative 57 Celsius, but the troposphere is heated by the surface, and that's very important. That's a big distinction between the troposphere, heated by the surface, and the stratosphere, which is heated by the absorption of ultraviolet light and the conversion of that UV radiation to infrared or IR heat. So the stratosphere, it warms up, and it warms up because of the absorption of ultraviolet light and its conversion to heat. The mesosphere, it gets colder again. There's hardly anything up there, very few molecules. So there's very little to absorb heat coming in from space or the surface. The mesosphere going from 0 degrees down to -90. And then the thermosphere, again, there's hardly anything up there. It's warmer at the top because it's exposed to the radiation from the sun. Nothing's filtering it. The thermosphere is like the first layer of filtering for our atmosphere. So the handful of molecules that are there are just getting pummeled with energy from the sun. So they're very excited, but there's only a couple, so it doesn't matter. And then in terms of function, we have the ozone layer going from around 18 kilometers up to about 50 kilometers, heated by the absorption of ultraviolet light, again. And then we have the ionosphere going from 80 kilometers to 480 kilometers, and that's absorbing gamma rays, X-rays, and a bit of ultraviolet. In fact, the auroras occur in the ionosphere because that's where they are absorbing that energy and getting excited. So some of the layers I mentioned are the same or occupy the same space. So if you're talking about it in terms of temperature, we call it the stratosphere. If we're talking about it in terms of function, we call it the ozone layer. Another bit of confusion is probably the thermosphere and the heterosphere. They occupy the same space, but if you're looking at it in terms of the composition of gases, we call it the heterosphere. If you're looking at it in terms of temperature, we call it the thermosphere. So I think that's a lot of the confusion with the layers and the names of the layers and why is this called that? It's the same space. Yeah, but if we're looking at the heterosphere, we're looking at the layers of gas, and if it's the thermosphere, we're looking at the decreasing temperature. So the names for the layers are based on the criteria, what characteristics or qualities of that layer you're looking at. Hours of day length. I posted a link to some cool slides. This guy, Brian Brettschneider, has produced about a gajillion maps of the season. So hours of sunlight on the summer solstice, if you're at the equator, every day is 12 hours long. In California, we have about a 14.5-hour day. And if you're above the Arctic Circle in this white area, the sun never sets on the summer solstice. Hours of daylight on the winter solstice would be 24 hours minus whatever the day length was on the summer solstice. So the places that had 24 hours of light, they get nothing. We had 14.5, so now we have 9.5 hours of daylight on the winter solstice. And again, just animation showing the shifting subsolar point from the southern hemisphere back to the equator, back to the northern hemisphere over the course of a year. Angles of radiation, that if you're at the equator, you're getting direct radiation, so it's very concentrated. And everybody else, as you move away from the equator, you can see that the angle of the sun's rays is getting less than 90 and less than 90, and the area that ray is lighting up, because the energy is spread out, is getting larger and larger and larger. Net radiation, you don't have to measure it. A lot of people were saying, I don't know how to measure it. You're never going to have to measure it. It's just the difference between incoming and outgoing radiation. So it's the difference between the energy coming in from the sun and the energy going out from Earth. Net radiation varies with latitude. The tropics have positive net radiation. The poles have negative net radiation. So in this region, more energy is coming in. And for those of you who are wondering, it's all measured with satellites. I'm never going to ask you to measure it. It's interesting. Yeah, it's interesting, but I'm never going to ask you to measure, because then I'd have to somehow track down the data set of incoming shortwave radiation, and then we'd have to track down a data set of outgoing long-wave radiation. So this area has a surplus. More energy is coming in here than going out. And then over here, more energy is going out from Earth than is coming in from the sun, because the energy comes in the tropics, and then it gets distributed to the poles by wind, by ocean currents. And there's a link to those maps. So those are the confusing topics, at least what seem to be the main topics of confusion. Hope that's helpful. If it's not helpful, please, please, please let me know so that I can redo the video or meet with you in Zoom hours and we can go over it so you understand it.